let's go. Vamos lá. Pode ir, Carlos.
Okay. Started.
Okay. Good afternoon, everybody. It's a great pleasure to introduce Dr. Mang Tia. It's a very good friend of mine. So we will continue our symposium. And I will make a brief introduction of Dr. Tia. And after that, I will give the word to him for the presentation. I will back up him with the support of Paloma and Marcos. And the questions and comments are very welcome. So I hope you will enjoy and make a lot of comments and questions, because Dr. Tia will give good thoughts about his career. Dr. Mang Tia is professor of civil and coastal engineering at the University of Florida, where he has been a faculty member since 1982. He received his PhD degree in civil engineering from Purdue University in 1982. His master's degree in civil engineering also from Purdue University in 1978, and the bachelor degrees, 2 degrees, one in mechanical engineering and another in civil engineering from the MIT. His areas of specialties are asphalt and concrete materials, asphalt, concrete, and composite pavements, accelerated testing of full-scale pavements, instrumentation for pavements and materials testing. He is a co-holder of a U.S. patent on a field permeability test apparatus for concrete, awarded in 1993. He has been for 3 times a recipient of Best Teacher Award at the Florida University, has been for 3 times recognized by the President of the University of Florida as one of the top researchers at the university. So yeah, we are in very good hands. So thank you, Mang. The word is with you. And after your presentation, I will come back with the comments and questions from the audience.
Okay. All right, let me see. Okay, can you see the screen now? Yes. Yeah, thank you very much, Professor Leomar Fernandez. Thank you for inviting me to speak at this prestigious School of Engineering of San Carlos of the University of Sao Paulo. It is indeed a great honor for me to do that. I have not visited your school, but I hope that in the near future, I will have a chance to visit your great School of San Carlos in person. I am speaking from the University of Florida, USA. This map shows the location of Florida in the United States. University of Florida is located in Gainesville. This map shows the location of Gainesville, which is marked with a green star in the map here. And on this map, you can also see the location of some famous cities in Florida, including Orlando. That's where you go to Disney World if you come to visit Orlando. There's Tampa, Miami, Jacksonville, and this is our state capital, Tallahassee. This is our beautiful University of Florida. The campus is characterized by beautiful red brick buildings and a lot of palm trees. And this is the historical Sentry Tower, which is a tourist attraction at the University of Florida. If you come to visit the University of Florida, people will take you there. This tower is over a century old. It's known as the Sentry Tower. And this is where our president the university president's office is located. However, the highest paid person at our university is not our university president. The highest paid person is our football coach. People are here very crazy about football. This is the University of Florida during a football game before the pandemic. Now, due to the pandemic, the football stadium is allowed only 20% of its normal capacity. And this is how the stadium looked like during a recent football game. If you look to the other side of the stadium, it looks like there's a lot of people, but it's actually filled with fake people. This is a picture of fake people in our football stadium. Okay, so that it looks like there's more people, but they're full of just images of people. Well, recently, about 20 people from UF football team, including the coach, tested positive for COVID-19, and the football game was canceled last weekend, and it has been suspended indefinitely for now, unfortunately. Well, I'm here to talk about concrete pavements, not football. Here's a famous concrete pavement in Florida, on the northern Florida. It's known as Interstate 10. Okay, Interstate 10, it's about 4,000 kilometers long, and it started from the Pacific West Coast in California, and it runs, all the way east to the East Coast in Florida. Okay, in Florida, this I-10 section, it's about 600 kilometers long, and it runs from on the western end, the Alabama state border. It runs through the state capital, Tallahassee, and it ends at Jacksonville on the east side. Well, construction of I-10 started in the early 1960s, and it continued through the mid-1970s. Well, during the planning for this highway, there was lobbying from the concrete industry people to build it with concrete. And there's also lobbying from the asphalt industry people to build it with asphalt. So, but finally, a compromise was reached. The western half, from Alabama to Tallahassee, would be built with concrete, and the eastern half, from Tallahassee to Jacksonville, would be built with asphalt. Okay. And this figure shows the typical pavement design used on the older section of this concrete pavement. It had 23 centimeter thick jointed concrete slab, and it had 30 centimeter of conventional stabilized subgrade. Unfortunately, no sub-drainage system was installed to allow water to be drained off this pavement. So as a result, pumping failure was observed on this concrete pavement. Pumping was due to water which is trapped under the concrete slab, and is pumped out of the edge of the concrete slab when heavy vehicles go over the slab. Pumping causes erosion of the subbase materials underneath the slab and creates voids underneath the slab, as you can see from this picture. Due to lack of support underneath the concrete slabs, cracking occurred. This is an example of cracking which was observed on that pavement. Well, because of this observed failure, some modifications was made to the design of the rest of the pavement which had not been constructed. So instead of using 30 centimeter of stabilized subgrade, in the modified design, it's replaced with 15 centimeters of lime treated subbase over 15 centimeter. I'm sorry, the first one was cement treated subbase over 15 centimeter of lime treated subbase. The idea behind this modified design was that this would make the foundation stronger and the subbase would be less erodible. However, this made the situation even worse. This was even, there was even more cracking on this pavement with a stronger subbase, as you can see from this picture. The use of the more impervious lime and treated subbase had actually worsened the drainage condition of the pavement and thus aggravated the pumping problem even more, as you can see from this picture. Well, several years later, in 1980, there was construction of another concrete pavement on this I-75, which runs north and south through Florida. Okay, and it goes south and all the way to Miami. Okay. There was a construction of a 46-kilometer, 6-lane concrete pavement in the county of Sarasota and Manatee, which is south of the city of Tampa, as shown in this map. Well, because of the problems they have seen on the I-10 concrete pavement, a new design was adopted for this pavement. An even stronger base was used for the concrete slab. The base used was a 15 centimeter Econocrete, as shown here in this drawing. The shoulder lane was also constructed with Econocrete, as shown here. Econocrete is concrete with relatively lower strength than normal concrete, but it's much stronger than the cement-treated subbase. It also used an innovative design of skew joints. Skew joint is joints that is not at right angle to the longitudinal direction. And it also used variable joint spacing. The slabs are of different lengths and spacings of 16, 17, 22, and 23 feet are used. Okay, this corresponds to 4.9, 5.2, 6.7, and 7.0 meter. The rationale behind the use of skew joint was that when trucks' wheels pass over the joints, only one wheel would pass over the joint at one time, and thus the impact effect would be lessened. And the rationale behind the use of variable joint spacing was that this would lessen the resonance effect. If the slabs are of different lengths, if they were to vibrate, they would vibrate at different frequencies, and thus the chance of all the slabs vibrating at the same resonance frequency would not happen. The Econocrete shoulders were tied to the concrete slabs with tie bars, And it was indeed what we can call a Cadillac design. Cadillac is a very expensive car, so this is an expensive design. It was a Cadillac design which should never fail. And it was like the Titanic ship, which should never sink. But just like the Titanic sank, this pavement failed miserably. Soon after the highway was opened to traffic, transverse cracking was observed, especially on the longer slabs. Later on, when structural analysis was performed to evaluate the effects of skew joint, it was found that the use of skew joint didn't really help. It actually increased the maximum stresses due to the acute angles of the slabs at their corners. And also pumping was observed from the supposedly non-erodible Econocrete base. We as university researchers had the opportunity to investigate the problems of these pavements. And I was the person wearing a white cap here in this picture. So we worked together with the engineers from the Florida Department of Transportation to investigate the causes of problems, checking for dowel bars with metal detector, checking ground slope to evaluate drainage condition of the pavements, performing falling weight deflectometer tests to evaluate the response of the pavement under various conditions. Thermocouples were used to monitor temperature variations within the concrete slabs. In those days, a chart recorder was used to record and plot temperatures measured by thermocouples, which were placed at various depths in the concrete slabs. These are a few typical temperature distributions in a concrete slab at different times in the daytime. In the daytime, the temperature of the concrete was higher at the top than at the bottom, as you can see from these plots. At night, it's the other way around. At night, the temperature is lower at the top than at the bottom. And this shows temperature distributions at different times at night. Well, at nighttime, when the temperature is lower at the top of the slab may curl up at the edge, as shown in the middle figure here. In the daytime, when the temperature is higher at the top of the slab than at the bottom, the slab may curl up this way, as shown in the bottom figure. And so if we apply the load on a curved slab, the induced stress could be much higher than the induced stress if it were applied to a slab with no temperature differential and fully supported, as in the top figure. To help with our evaluation, we developed a finite element model called FECONS for analysis of concrete pavement under the combined effects of loads and temperature differentials in the concrete slab. It also had the capability to model the effects of joints and edges, and also model the behavior of concrete slabs, which is either bonded or not bonded to the base layer. So with this finite element model, we are able to do a lot of analysis. Analysis was made to determine the most critical loading condition at night. At night, where would we place the load so that we get the maximum stress? And what we found is that at night, when the slabs tend to curl up at the edges, the most critical loading condition is when we place the load at the corner, as shown here. Here's it shows an axle load with two loads, for one axle. If the load is applied here, when we have a negative temperature differential, we're gonna get the maximum stress. Okay. And so how much load should we put on, and how should we model the temperature differential? Well, our study shows that, well, if we put the maximum allowable axle load, which is 22 kips, and we use a condition of a typical maximum negative temperature differential at night, and that happens to be around negative 10 degrees Fahrenheit. Okay, so we would place the load here, 22 kip axle load at this corner, and we use a temperature differential of negative 10 degrees, and we get we can calculate the stress, and we can look at the maximum stress at night. Okay, and in the daytime, we also do analysis for daytime condition when the slab is curled up at the center. Okay, under that condition, the worst condition, the most critical loading condition is when the axle load is placed at the meet edge, as shown here. So the one wheel would be touching the edge, the other one is, at 6 feet away from this wheel here. This is when we have the maximum stress. Okay, and in the daytime, typically, if we have a positive 20 degrees Fahrenheit, we have the worst condition. So to determine the worst maximum, the worst stress in the daytime, we'll place this load here, and we use a temperature differential of plus 20 degrees Fahrenheit to determine the maximum stress. Okay, well, how do we model the temperature differential or the temperature distribution? Well, we can approximate by a quadratic equation, as shown here. But to simplify the calculation procedure, the temperature distribution was approximated by a linear distribution, as shown by a straight line here. Okay, it's much easier. We model as straight line instead of this quadratic equation. Well, when the temperature distribution is assumed to be linear, the calculated maximum stress tend to be higher for the daytime condition and lower for the nighttime condition. The maximum stress in the daytime condition is usually higher than that at night. And thus, if we use a linear temperature distribution, we will get a higher estimation, which is a more conservative estimation of the maximum stresses. So it's okay to use a linear approximation, because in that way we'll get a more conservative estimate of the maximum stress. Well, when temperature differential in a concrete slab is not considered in stress analysis, as shown by the plots at the bottom of this figure here, the stiffness of the subgrade has a significant effect on the maximum stress. This is a plot of maximum stress versus subgrade stiffness. As the subgrade stiffness gets higher, the stress goes lower, and this is our conventional theory about the effect of subgrade. If you use a stiffer subgrade, the stress would be lower, and that's true if there's no temperature differential. but when temperature differential is considered, the stresses are much higher, but also the subgrade stiffness has less of an effect if temperature differential is considered in the analysis. So using a stiff subbase would not help in reducing cracking in the pavement slabs. Here's an example of a cracked slab on a pavement with a stiff subbase. And concrete pavement with stiff subbase could crack even more, as we have seen from our observation. So we can summarize by saying that when the effects of thermal gradients are considered, the effects of subgrade stiffness has very little effect on the maximum stresses in the concrete slab. The use of a stiff subgrade or subbase may not necessarily improve the performance of a concrete pavement. When temperature differential in a concrete slab is not considered in the stress analysis, slab length has no effect on the maximum stresses. However, when there is a temperature differential in the concrete slab, the concrete length could have significant effect on the maximum stresses. These are plots of maximum stress in a concrete pavement as a function of slab length for different temperature differentials. As you can see from these plots, when there is a temperature differential in the concrete slab, the maximum stress increases as the slab length increases. Thus, we can summarize by saying that when thermal gradients exist in a concrete slab, the maximum stresses increases with increasing slab length. And this conclusion was validated by our observation of cracking in the concrete pavement on I-75 in Sarasota and Manatee counties. The slabs of longer lengths of 6.7 meter and 7.0 meter cracked more than the shorter slabs of lengths of 4.9 and 5.2 meter. This figure shows plots of maximum stress at the critical loading condition as functions of elastic modulus and coefficient of thermal expansion of concrete. When temperature differential in the concrete slab is considered, the maximum stresses are also affected by coefficient of thermal expansion, as you can see from the plot here. As the coefficient of thermal expansion increases, the maximum stress increases, and also it increases as the elastic modulus increases. The maximum stress affected by the elastic modulus of the concrete, as shown in the previous slide, and the data obtained from I-75 concrete pavement in Sarasota and Manatee counties show that the concrete with higher elastic modulus show higher percent of cracked slab. These are data from our field observation. When we plotted elastic modulus of the concrete versus the percent cracked slab, it shows that the concrete with higher elastic modulus actually cracked more. Usually, concrete with higher strength is accompanied by higher elastic modulus, as shown in this plot of elastic modulus versus compressive strength of concrete. Thus, using a stronger concrete may not necessarily give us better performance, as the performance of the concrete pavement is also affected by the elastic modulus and coefficient of thermal expansion of the concrete as well. We can say that maximum temperature low induced stresses increase as the concrete modulus and coefficient of thermal expansion increase. To evaluate the potential performance of a concrete pavement, we can compare the maximum stress with the flexural strength of the concrete. A concrete giving a lower maximum stress to flexural strength ratio would be less likely to crack and would give a better performance. The design of the I-75 concrete pavement in Sarasota and Manatee counties is shown on the left here. It had 23 centimeter of concrete over 15 centimeter of Econocrete base, and there was no bonding between the concrete and the Econocrete base. Critical stress analysis using a 22 kip axial load and a temperature differential of plus 20 degree Fahrenheit in the concrete slab gave a maximum stress at the bottom of the concrete slab, and the stress was equal to about 78% of the flexural strength of the concrete. If the concrete slab were bonded to the Econocrete layer, the concrete and the Econocrete layer would act as one thick slab, and under the same load and temperature differential, the computed maximum stress would occur at the bottom of the Econocrete layer, and that maximum stress would be equal to only 67% of the flexural strength of the Econocrete. Unfortunately, the concrete slab was not bonded to the Econocrete base in that concrete pavement. If they had been bonded together, this pavement could have much better performance according to our prediction. We can make the following summarizing statements from our study. When critical temperature low conditions are considered, the effects of some design parameters are seen to be substantially different from those held by conventional pavement design methods. The maximum computed stress under the critical condition is seen to increase substantially as the slab length, elastic modulus, and coefficient of thermal expansion of concrete increase. The maximum stress is seen to be less affected by variation in subgrade stiffness and joint stiffness. A composite pavement with a bonded interface is seen to have a much lower maximum stress than that with an unbonded interface. Using a wider slab that extends some distance into the shoulder length can reduce the maximum stress in the slab substantially. Using a thicker slab is the most effective way to reduce the maximum stress. And as most people already know, that good subdrainage is essential to ensure good pavement performance. These plots shows the maximum stresses as a function of slab thickness. The plots on the lower part of the figure are for the condition of no temperature differential in the concrete slab. The plot on the upper part of the figure is for the condition of temperature differential of plus 20 degree Fahrenheit. In both cases, the maximum stresses decrease significantly as the slab thickness increases. This is a typical design used by the more recently built concrete pavements in Florida. It has a thick concrete slab with a thickness of 33 centimeter. The concrete extends 2 feet, which is equal to 61 centimeter, into the shoulder length in order to reduce the maximum stress on the concrete slab. The new design uses sub-base materials which have good drainage characteristics. The new design also incorporates edge drains from here to drain off the water which may get under the concrete slab. Okay, and so from all the lessons we've learned, the design used now is much better. Next, I want to share the result of a recent study on the evaluation of concrete pavement life expectancies in Florida. First, a little bit on the background and objective of this study. In Florida, the initial design for new construction for both asphalt and concrete pavements is 20 years, while the rehabilitation period of asphalt varies from 8 to 20 years. That of concrete pavements varies from 20 to 25 years. Increased traffic on roadways caused due to maintenance-related traffic delays and increasing construction costs have led the Florida Department of Transportation to evaluate various concrete pavement designs which would yield service lives of 50 years or more. And I would like to present 4 of the main tasks in this study. I won't read them as I will present them one by one as we go along. In the first main task, the Mepdg, which is the Mechanistic Empirical Pavement Design Guide model. Now it's known as the Wed Pavement ME Design. This model had been calibrated for the Florida condition, and this model was used to analyze, number one, the performance of 3 typical concrete pavement designs in Florida, to evaluate their suitability for use as long-life concrete pavement, and 2, we also evaluate the effects of various design parameters on their performance. The 3 design evaluated were designated as Type 1A, Type 1B, and Type 2 in this study. This is Type 1A design. It has PCC slab of very thickness, has 10 centimeter of asphalt treated or cement treated permeable base, 5 centimeter of structural asphalt concrete, and 30 centimeter of a stabilized subgrade. Here's the design for Type 1B. Has concrete slabs of different thickness, 10 inches of asphalt concrete base, and 30-inch of a stabilized subgrade. And Type 2 design also has very concrete slab thickness, 15 centimeter of special stabilized permeable subbase, and 137 centimeter of A3 soil. It's a permeable soil. Okay, so these 3 concrete pavement designs were evaluated using the Mepdg model, which, as I mentioned earlier, has been calibrated for Florida condition. The design life of the concrete pavements to be analyzed by the Mepdg model was set to be 50 years. The outputs of the Mepdg analysis gives the predicted performance of the pavements in terms of International Roughness Index, IRI, joint faulting, and transverse cracking over the design period. If one or more of the predicted distresses at the end of the design period exceed the acceptable threshold values, the analyzed pavements would be considered to have failed for the design period. The input threshold values used are given here. Okay, and we need to have an initial IRI, and the initial IRI was set to be 58 inch per mile. This is the threshold value without consideration of reliability level. So we assign a reliability of 95%. Okay. When the reliability is set to be 95%, these threshold values are now much lower. So at the end of the design life, if the predicted distress is higher than these threshold values, we would consider that the design is not adequate. Okay. The factors evaluated in our analysis include slab thickness, concrete flexural strength, aggregate used in the concrete, types of base material, stiffness of base material, thickness of base, and erodibility of base material, and also friction between base and the concrete. And what we found is that out of all these factors, the 3 most significant factors were: 1, the concrete slab thickness, concrete flexural strength, and the aggregate used in the concrete, which affects the elastic modulus and coefficient of thermal expansion of the concrete. 3 typical concretes used in Florida made with 3 different aggregates were used in this analysis. These 3 aggregates were: 1, Brooksville limestone, which is a porous limestone in Florida, a Carrara limestone, which is a dense limestone, and river gravel. And typical properties of these concretes, as obtained from previous studies, were used as inputs for the concrete material properties. And this table shows the typical coefficient of thermal expansion of concrete made with these 3 aggregates. It can be seen that the concrete made with the Brooksville limestone has the lowest coefficient of thermal expansion, and the one that used river gravel has the highest coefficient of thermal expansion. A flexural strength of concrete of 650 psi, which is equal to 4.5 megapascal, was used in the analysis. In a previous study by UF, the elastic modulus of Florida concrete was related to the flexural strength, unit weight, and type of aggregate used by various regression equation. We see here the regression equations which relate the density and the flexural strength to the elastic modulus. The developed equations, as shown here, were used in determining the elastic modulus of these three concretes used in the analysis. This table shows the calculated elastic modulus of these three concrete with a flexural strength of 650 psi. So basically what I'm saying is that when the flexural strength changes, the elastic modulus would change accordingly, and we use these equations to estimate the elastic modulus at different levels of flexural strength. Okay, so this table shows the results of the Mepdg analysis. Okay, there's a lot of information here, and what I want to point out is that, well, it shows the terminal distresses, okay, and it shows that up here it shows the required thickness in order to meet all the criteria. Okay, and let me try explain it a little bit more. Okay, first of all, the an initial average annual daily truck traffic of 4,000 and a concrete flexural strength of 650 psi were used in this analysis. Okay, so here we have the three designs, and we have concrete made with three different aggregates. So all these concrete have the same flexural strength, but because they were made with different aggregates, they have different coefficient of thermal expansion and different elastic modulus, so their predicted performance are different. So they all have the same strength, but their performance are different because their elastic modulus and coefficient of expansion are different. Okay, so you can see, the results are fairly similar for the three different designs, but it's different from one aggregate to another. If we use this good aggregate with a low elastic modulus and low coefficient of thermal expansion, we only need thickness of 13 inches. Okay, but if we use river gravel, and the concrete is as strong as the other one, but because it has a high coefficient of thermal expansion, especially the coefficient of thermal expansion, and also it has relatively higher elastic modulus, the performance is not as good, and we would need to have 16 inches versus 13 inches. Okay, and the results are similar for the other three designs, and we can see that, well, the key thing here is to use the right aggregate. Okay, it's not the strength, it's the aggregate. If you use the right aggregate, you can have the same strength. The concrete is going to perform much better because of the aggregate, the right kind of aggregate you use, because the concrete has a lower coefficient of thermal expansion. So big difference, difference between 13 inches versus 16 inches. Right? So now the rest of the analysis is going to be done using this good aggregate. We want to see if we can really design a concrete pavement that can last for at least 50 years, and let's do it with this good aggregate. Okay. Okay, so now we try to look at the effect of flexural strength Okay, analysis made with this concrete using this good aggregate, and we vary the margin of rupture from 600 psi to 700 psi to 800 psi, and we want to see if increasing the margin of rupture, which is the flexural strength, does increasing the flexural strength make a difference? And the answer is yes. Yeah, when you increase the flexural strength, as you can see here. Okay, so when the flexural strength is 600, it all fail. When we see a red number here, it means it failed. It fails. All of them fail for a thickness of 13 inches. Okay, but if we increase the flexural strength to 700 psi, then we only need 12 inches, and it would last for 50 years. If we go up to 800 psi, we only need 11 inches. So let me repeat this. If you use the same concrete made with the same aggregate, if you increase the flexural strength, the performance would be better. Okay, well, the previous analysis was done using an average daily truck traffic of 4,000, which is relatively low traffic volume. Well, can we design pavement with extremely high traffic, and can it last for 50 years? Okay, so that's what we did next. So we use an extremely high daily traffic truck volume of 17,000. So basically, the 17,000 trucks pass through the pavement in a day. Okay? And we use this best aggregate for our concrete. Okay, and so we ran the analysis to see how long it would last. Okay, if we have different thicknesses, and here's a different thicknesses. This shows the expected life. Okay, and you can see that, well, we use this good concrete made with this good aggregate. It can be done if the thickness is 13 inches. So here, 13 inches, the life expectancy is over 50 years for all three designs, and the type 2 is the relatively better than the other two. So, but all of them would work. Okay, so the key thing is you need to have enough thickness, and you need to have the right concrete, not just strength. In the past we always think about strength, make it stronger, but you need to have the right aggregate, otherwise it won't work. Okay, we have the right aggregate, and of course you need adequate strength. In this analysis, we use a flexural strength of 650 psi, which is equal to 4.5 megapascal. Then it would last for at least 50 years. Okay, and so we can make these conclusions that the predicted performance of the pavement appear to have improved slightly with an increase in base thickness. The type of base material and stiffness of the base material appear to have no significant effect on the predicted performance. And also using different erodibility factor and friction factor for the base material appear to have no significant effect on the predicted performance according to the results of our Mepdg analysis. Okay, next we want to, those are analysis. Next we want to look at some real data. Okay, where can we find some real data? Well, the ASTE keeps some long-term performance data. They've been monitoring various pavement sections, and so we got the data from this database, the long-term pavement performance database was used to evaluate the effects of various factors on performance of jointed plain concrete pavements in the U.S., with emphasis on Florida and its neighboring states. And we also done critical stress analysis using the FECONS program on the selected the joint plain concrete pavement, this JPCP, plain concrete, joint plain concrete pavement sections. And we use this critical stress analysis to determine the maximum stress in the concrete slabs under critical load and temperature condition. The maximum computed critical stress for each condition was divided by the margins of rupture of the concrete to determine the stress to strength ratio. And there were a total of 26 jointed plain concrete pavement sections in the region that is similar to the condition in Florida. It's known as the wet and no freeze climate zone. Okay, and this map shows the location of the pavement sections that we got the data from. And there's two of them have two test sections marked in red were excluded due to incomplete data. Thus, only data from 24 test sections were used in the analysis. Okay, in the critical stress analysis, using the pavement parameters and material properties for these 24 test sections, maximum stress under critical low temperature condition was computed for each test section, and the maximum stress caused by a 22 kip axial load applied at the middle of the edge of the concrete slab when there was a temperature differential of 20 degree F between the top and the bottom of the concrete slab was computed. This represented a critical loading condition as reported by previous studies for Florida DOT. And the FECONS computer program was used for the stress analysis. This shows the finite element meshes used and the location of the applied load for the various slabs with different slab lengths. And this shows a plot of computed stresses from the critical stress analysis. Maximum stress from this analysis was used. The performance of the test sections were quantified by an IRI deterioration rate. The IRI deterioration rate was computed by dividing the change in IRI by the number of years and the average annual traffic in number of ESOs. So a higher IRI deterioration rate represents worse performance. This is a plot of the computed maximum stress versus IRI deterioration rate. A higher computed maximum stress is related to a higher IRI deterioration rate. However, the correlation is not very good as seen from this low R square value. When we divided the maximum stress by the flexural strength of the concrete to obtain the stress to strength ratio and plot stress to strength ratio to IRI deterioration rate, we got a better relationship with slightly higher R square value. So as the stress to strength ratio increases, the IRI deterioration rate also increases. Findings from the critical stress analysis are summarized as follows. The computed critical stress to strength ratio was found to be the most significant parameter which can be related to the performance of the LTPP pavements. A lower stress to strength ratio is related to better observed pavement performance. The better performing pavements were noted to have a computed stress to strength ratio of less than 0.7. 0.7. This figure shows plots of maximum stress versus margins of subgrade reaction for different slab thickness from the critical stress analysis. It can be seen that when the slab thickness is 11 inch or higher, increasing the subgrade modulus actually increase the maximum stress in the concrete slab when we calculate the stress using the critical loading condition. These are plots of calculated maximum stress as functions of elastic modulus and coefficient of thermal expansion, the CTE, coefficient of thermal expansion, from a critical stress analysis, and it can be seen that the maximum stress increases as the elastic modulus increases and also as the CTE increases. These are plots of stress to strength ratio as function of margins of rupture and slab thickness. Concrete made with the best aggregate among the three. Okay, they're not necessarily the absolute best, but among the three, the best aggregate of the Brooksville aggregate was used in the analysis, and the relationship between the elastic margins and margins of rupture of the concrete was used to determine the elastic margins of the concrete needed in the analysis. So when you assume a certain flexural strength, you have to estimate the elastic modulus of that concrete, and we use that the equation that we developed earlier to make those estimations. And so from the plot, it can be seen that we have a concrete made with the same aggregate. Increasing the margins of rupture of the concrete will reduce the stress to strength ratio and thus improve the performance of the concrete pavement. Didn't we already conclude that? Well, we conclude that from the Mepdg analysis. Now we conclude it from the critical stress analysis. Okay, here's a summary of the findings from the critical stress analysis. The most significant factor affecting stress to strength ratio are the concrete slab thickness and the concrete properties, which include the elastic modulus, margins of rupture, and coefficient of thermal expansion. Variations in the base and sub-base properties were found to have minimal effects on the stress to strength ratio for concrete slab thickness of 11 inches or higher. These observed results agree well with the findings from the Mepdg analysis. These findings is that the most significant factors affecting performance of the concrete pavements are the concrete slab thickness and the concrete properties. And similar to the results of the Mepdg analysis, when the same aggregate is used in the concrete, increasing the flexural strength of the concrete will result in better predicted pavement performance. So the third task is life cycle cost analysis, the cost estimate for these three pavement designs with concrete slabs varying from 10 inches to 14 inches were developed. The predicted service lives of these pavements were based on results of the Mepdg analysis using a concrete made with Brooksville aggregate and assuming a margin of rupture of 650 psi. Okay, this table shows the estimated total cost for 10 miles of 4-lane highways using type 1A design. Okay, and also different discount rates were used to figure the annual cost. Okay, so this shows, okay, like this is the slab thickness and this is the expected life and the annual cost. So what would give us the least annual cost? Okay, the analysis, this shows the annual cost, right, based on different discount rate. If a discount rate of 3.5%, that's kind of the interest rate that we pay if we borrow money. If a discount rate of 3.5% is used, the minimum annual cost is here. Here's the minimum annual cost. If we have a slab thickness of 13 inches, it would last for 51 years, and we have the lowest annual cost. Okay, if you have a thinner slab, the annual cost would be higher. If you have an even thicker one, it's going to be higher. So this is the optimum design. But the optimum design depends on the discount rate. If there's no interest, which is not realistic, okay. So if there's no interest, then the lowest one is to build as thick as possible. If you don't have to, if you borrow money and you don't have to pay interest, of course, you can borrow as much money as you want, and so this won't work in real life. Okay. So this is a more realistic interest rate today. Okay, if it's 5%, then the lowest annual cost would be if we use 12 inches. Okay, and the expected life would be 42 years. Okay, so this is for type 1A design. We have similar data for type 1B design. They are kind of similar, so it looks like the 13-inch would work the best if we have an interest rate of 3.5%, and for type 2 design, right, kind of similar. We have an interest rate of 3.5%. The best design would be if we use 13 inches, it will give us a expected life of more than 50 years. Well, if we compare between these three types of design, type 2 is better than the other two. Okay. But all of them can give us a life expectancy of over 50 years. Okay, we can summarize the findings here. Type 2 design has the lowest cost estimate, and when cost of interest was not considered, we can use a much thicker slabs. But if we have an interest rate of 3.5%, then we can go with 13 inches, which is equal to 33 centimeter, and the expected life would be 51, 50, or 56, depending on the design. So the design 2 is the best. Okay, so here's our recommendation to Florida DOT. Okay, the 3 typical Florida concrete pavement designs evaluated in this study can be used as long life pavements if the slab thickness is adequate and the concrete has low elastic modulus, low coefficient of thermal expansion, and adequate flexural strength. So the key thing is not just flexural strength, but we need to have low elastic modulus and low coefficient of thermal expansion. Okay. If you just put in any type of concrete with enough strength, it may not work. Among the 3 designs, type 2 is the best, in terms of longest expected life and the lowest cost. And so we recommend that, if possible, use type 2 design for use as long life concrete pavements in Florida. But this requires a use of A3 soil, which is a good soil, permeable, good strength. But if it's not available, we can go with the type 1A or type 1B as well. Okay, so the key thing is to need to have enough thickness. If we want it to last for 50 years with heavy traffic, you need at least 13 inches. Better yet, if we have 14 inches. Okay, this would be equivalent to 33 centimeter, and 14 inches equal to 35.6 centimeter. If we use 14 inches, we have an extra either half an inch or 1 inch, can be considered as sacrificial concrete for future grinding during the life of the pavement to restore its right quality, texture, and remediate faulting. Okay, after many years, concrete pavement tends to have some faulting, and we can grind it and restore its writability. And we have the extra half an inch and 1 inch every time. We can grind off a quarter inch, and we do it about 2 to 4 times. The present construction specification seems to be adequate. We just need to design the concrete mixtures accordingly. Okay, so 650 psi of 4.5 megapascals at 28 days seems to be a good strength to use. The key thing here is to use an aggregate which will give us a low elastic modulus and low coefficient of thermal expansion. How do we know? Well, we can look at past records of test data. If not, we have to run some tests in the lab. So what are the key things we need to look at? We need to look at flexural strength, elastic modulus, and DTE, the coefficient of thermal expansion. And usually we measure that at 28 days. And how do we know that it's going to last for 50 years? We can run this Mepdg analysis. Now it's not called Mepdg because in the past this software is free. Now it's no longer free. So it's called the ISTE ME design. Okay, so it's not free anymore. So if you want to get it, you have to pay a license fee. Okay. Okay, so we can run the analysis to, if you have all the material data and the traffic, we can use this software, this ME pavement design software, to determine how long it's going to last. Determine the expected life, and does it have an expected life of at least 50 years, using the properties of the concrete. If the predicted life of the pavement is at least 50 years, the concrete mix would be acceptable for the project. If it's not, if the predicted life is less than 50 years, a new concrete mix can be designed by either specifying a higher flexural strength or using a different aggregate. And if possible, try to use an aggregate that would give us a lower coefficient of thermal expansion. And step 1 through 3 would be repeated until an acceptable concrete mix for the project is obtained. And it's we also recommended that FDOT establish a database of concrete mix designs which are acceptable, so that you don't have to design the mix every time. You know, we have a good database for use in long life concrete pavement, so that the optimum concrete mixes can be designed and selected for selected efficiently for this purpose. Okay, so that's it. So what is the message I am preaching? Okay, the message I'm preaching is that concrete pavement would perform better if you use if the concrete use the right kind of aggregate that would give you a low coefficient of thermal expansion and also a relatively low elastic modulus. And the second thing I'm preaching is that don't just try to increase the subgrade stiffness. Okay, the subgrade stiffness is not going to help too much. You need some stiffness, but if you have problems, don't try to increase the subgrade stiffness. Okay, so the message is very simple, but we need to do it. We need if you believe it and then apply it, and you see that it's going to work. Thank you very much. I can take questions now. I can unshare now, I suppose, right? I can.
Okay, Mang.
Okay, I'll stop presenting, and I'll see if there are any questions.
Okay.
Sorry, I didn't use 2 hours, but I thought if it's more than 1 hour and 10 minutes, people will lose interest.
Okay, it was really great. Thank you very much for your very broad presentation, addressing many factors that affect the concrete pavement performance. I'm sure that the audience, starting with me, enjoyed and learned a lot.
Oh, thank you.
And as you mentioned, for us, it will be also very good, very nice to have you here in person. And in March, the graduate program, our graduate program, decided to have a partnership. And the partners would come to stay with us, lecturing and supervising. And
okay.
You are my partner, so
yeah, this arrangement of doing things over the online seems to work fairly well. Yeah. So it's
to have you here.
a lot of time not having to fly over there.
the support, the financial support to have you here. We have to.
Yeah. When the pandemic is over, we meet in person.
As soon as possible after the pandemic, we will restart thinking about our partners, and I hope to have you as soon as possible. We have some questions. As I told you, there is a delay, so I'm not sure if you can read, but
I'm kind of new to this platform, so if you just read me the question, and I'll just because I don't see the question right now, so just read me the question. Yeah.
Okay, it's in the chat.
Other
questions, but I can also read. One of our students is thanking your very good presentations.
Thank you.
Well, the first question is, do you consider in your calculation the drying shrinkage? The drying shrinkage?
Okay. Yeah, that's a very good question. And actually, we did not add the drying shrinkage. This could complicate things a little bit more. Okay. Yeah, that's a really good question. In our analysis, we just assume the fact we just analyze the fact of temperature and not drying shrinkage. Yeah, that it could add to it. It could add to it or it could subtract to it. Okay, but it could add to it and make it worse.
Okay. The second question is, in your opinion, which is the minimum compressive strength for a cement-treated base?
Oh, okay. Yeah. So, yeah, here we, as I said, the strength seems to have very little effect on the performance. Okay. So it's more like for construction. If can you construct the concrete pavement well with the subbase that you have? Okay. Yeah. So yeah, I don't want to give you an answer for the minimum strength. Yeah. It's more like if it's adequate, it can support the construction equipment.
Let me correct myself, because I said John Pioli, because I was John, another student, made some questions, but the questions I read is from Paulo Fernando Araújo da Silva, and he has a third question. How do you define adequate concrete? Could you put the number?
Yeah. So as you can see, the flexural strength does affect performance, right? And so when we do the analysis with different flexural strength, we get different predicted performance. Okay, and what for a long life pavement, it seems to be like the 650 psi or 4.5 megapascal in flexural strength seems to give us adequate performance in terms of long life concrete pavement. Yeah. So I would say that somewhere around 4.5 megapascal in flexural strength would give us a fairly good concrete.
Okay. Now I have the questions from John Pioli. For design purpose, what do you recommend for a stress analysis, assuming linear or non-linear temperature gradient over the slab thickness?
Okay. Yeah. So with our FECONS program, it can only do a linear temperature distribution. If we do non-linear, we have to do it by hand. We do the calculation and we have to do some adjustment. Okay, and so as I presented in this presentation, and when
linear is good enough.
In the daytime, when you assume it's linear, you actually get a higher number than a non-linear one. Okay, so since linear approximation makes life easy, we just use linear, and we get an estimate stress which is slightly higher than what we would get if we use a non-linear. If we use a non-linear, well, at least for what we did, we could modify the program to do it. So the stress would actually be slightly higher if it's lower in the daytime.
Okay.
Yeah. So to be more accurate, of course, non-linear would be better.
Okay. The second question is, What software do you recommend for stress analysis in concrete pavement? Do you recommend using ever Finite element FE? Ever FE?
Yeah, so we have one that's called FECONS, right? Yeah, and there's many others. There's one that was developed by University of Illinois, which later on was used in developing of this Mepdg. You know, I don't know what it was called earlier. It was ARIS, right? Is that what you were saying? Yeah, yeah. So if you use the ASTE one, it would give you a predicted performance, not just stress.
Okay.
Yeah. So yeah, I think for design purpose, you know, the ASTE ME, which is our formerly called Mepdg, would be the one that we would use.
Okay, and I will ask the questions of Marcus prior to the third one from John. In addition to the drainage problems on the I-10, could the fact of the shoulder was built with asphalt have an influence on pavement performance? Or
Okay. So the was that the question, like if the base or sub base it's asphalt, right?
no, he's mentioning that the shoulder was built with asphalt.
Oh, okay. Oh, yeah. If it's built with asphalt versus if it's like Econocrete, right?
Yeah, that's it.
Yeah, yeah. So my opinion is that the Econocrete does not help. You know, so you're. I think you're better off with asphalt shoulder. It's easier to maintain.
Okay. And the third questions from João. Do you recommend using granular base courses in concrete pavements or only cement treated bases?
Yeah, granted, well, the experience we had in Florida, the cement treated base had some problem, you know, especially if it's not really doesn't have good drainage characteristic. Granular base would be better for drainage purpose. Yeah, yeah. As you can see at the very beginning, I show the failures we have with the cement treated sub base. The pavement with the cement treated sub base had failed fairly badly because of the drainage problem.
Okay, so related to drainage, there is at first a comment from Paulo Fernando Araújo da Silva, and after one question. In his opinion, drainage is not an obligation if you don't have cracks, joints, because joints are sealed, and the joint between asphalt and concrete joints are sealed. What's your opinion about the drainage?
Yeah, so I think no matter how you seal it, water will get under the pavement somehow. You know, water has to drain somewhere, right? Yeah, so just sealing the joint is not going to eliminate the need for sub-drainage installation, right? Yeah, so we see that a lot of pumping still occur, and all the new pavements all have joints that are sealed, right? And some of them still have pumping problem if you don't get the water out. We can't prevent water from getting in. You know, the seal then can stop with a little bit, but not all of it.
Okay. And the Econo concrete is the same of RCC or
RCC, roller compacted concrete. Okay, it's not the same. Econocrete is a concrete that's made with some shell. This is some marginal aggregate. Okay, yeah, it's just used in local areas, Florida and maybe some other local areas.
Lower quality concrete.
Yeah, lower strength concrete.
Local materials. Okay.
Yeah, right.
Okay, Meg. As far as I can see
Okay. Okay.
And I hope you enjoy.
Well, yeah, those are very, very good questions.
Okay, and thank you so much for.
Well, thank you all so much for inviting me.
Really good. Our coordinator is thanking you, and I'm sure he enjoyed a lot. So.
Okay. Yeah.
When you are in Brazil, you will be in contact with him.
Oh, okay. Yeah. I hope this pandemic will go away soon. Yeah.
Yes. Okay. Say hello to Maria and the kids, and thank you very much.
Hello to kids. And, yeah, it was nice meeting them this past December, right? You were here last December.
Yes. Okay. Thank you very much.
Yeah, you're most welcome. Yeah, nice meeting you all, Pamola, and yeah.
Thank you, Paloma. Thank you, Carlos and Mark.